given by the Professor Wen-Chen and the academic Silica. He also the host, the organizer. I'm thinking his topic is very well fitted in this summer school. So he will talk about he will do the Drell-Yan experiment to determine the PDF, TMD, and the GPD. So let's welcome the speaker.
Actually, it's a kind of embarrassing for the organizer to give a talk. Yeah, so it's kind of like a self-recommended. But in any case, because we have a very good lecture, but there are many theories, so I think maybe it would be helpful to arrange some seminar talk more focused on introduce the status of the experiment. So I think you can feel pretty much relaxed. There is no complicated formula in my talk. I more or less give you some. I will first give you some kind of maybe history. Chang, can you turn off the light? Sure. Thank you. And a very basic formalism about the Drell-Yan process. And then I would go quickly to tell you a very naive, based on very naive Drell-Yan process, which is actually electromagnetic interaction on the most naive model. And what's it's actually quite become a very successful model, but also on the other hand, there is some kind of failure. So what was that when you later on compare, when you check using from the experimental observation, what kind of the thing is failure? And then by further taking into account the QCD effect, actually bring a lot of the improvement for that. And then based on the Drell-Yan process, actually can be used as a very powerful experimental tool to explore this PDF or TMD and even the GPD. Sorry, I modified. I just changed the title a little bit aggressive. I want to include also GPD like this, and I will come to the summary. Okay, so this is actually the one of the very first experiment that was performed at the AGS, at the Brookhaven. So that was using the something like a 20 GeV proton beam to hit the target. And the goal is want to measure they search for the vector meson. So something like a W or a Z over there. Okay, and the experiment was then performed and looking into whatever is generated over there, but I look at the Dimuon. And then form the Dimuon spectra over there. So this was kind of the plot given by this experiment over there. And what they observe is actually at the large mass here, they see some kind of the shorter. And unfortunately, due to, at that time, there's bad momentum resolution. So they actually missed the evidence of the gypsy, as you will see in a few more slides. And however, there kind of another interesting thing is actually this cross-section dropped very rapidly. They making an estimate is something like in the mass of one of the inverse fifth power with this Dimuon mass. So this is still something which is not quite known. Then at that time, there's two theorists. Drell, I think if you do the study, it's the Bill-King Drell, they write a very famous textbook, and the other is Yuan. And they making some well-known publication about, they try to explain what kind of things, what heck going on for this kind of a very sharp dropping of the production cross-section as the mass of the Q squared over there. And the naive picture actually they're going on is actually the quark and the anti-quark. Of course, at that time, there's no concept of quark. So they applied like a parton. So the parton actually get interacting from two separate hadron and then get into this virtual photon, and then go to the dilepton peak. If you pay attention to this number of the journal, this is PIL 25316, and the experiment is 251523. So you can see how active the series is. They published the explanation of the experimental data even before the data was officially published. Okay, so that was something interesting. And here I want to specifically bring your attention to the second author, which is Yan Dongmao. So he is actually Taiwanese. So he graduated from the National Taiwan University. And even about 30 years ago, he actually visited our institute here. So that was almost 30 years ago. And right now he already retired from the Cornell. So that was normally you call Drell-Yan. The Yan is actually his Taiwanese. So I just want to bring this fact to the young student here, in case you don't know. Okay, then I get some kind of a quote from some article written by Yan. So he said that Sid and I get interested in this process for two reasons. Okay, we are looking for the application of pattern model outside of the DIS, and we want to understand if the rapid decrease of the cross section with the muon pair mass can be reconciled with the point-like cross section observed in the DIS, the electron scattering. Okay, so the key idea in this approach is actually the impulse approximation. I think in Kumano-san's talk yesterday, he actually mentioned that is you actually put into a probe into your system, but this probe has to be, reaction time has to be much less than the whole interacting parton inside it. So the more or less the constituent or the parton you are going to be probed can be treated like a free. Then the overall interacting cross section based on this impulse approximation can be very simply written down as a probability of it's actually in terms of the Professor Mulder's is you separate the hard part with the soft part. So right now the hard part you can evaluate this is some particular parton configuration, and then the soft part is actually the one you would not be able to calculate. It was normally called like PDF. Okay, and then it's interesting to know that our original crude fits doesn't even remotely resemble the data, right? If you take a closer look, this this drop doesn't really fit the data at all. However, they say that just because the paper, the model simplicity, and also the belief that future experiment will be able to either confirm or rule out this model, so they simply proceed to getting out of this. So in some sense, if you perform doing the theory, so try to, again, don't hesitate if you have some thinking, just proceed about it. Okay, so here just for the completeness of the formalism, so I include a couple of slides here, but I don't actually want to go through. So we have the two hadron get together, and one of them contribute either quark or anti-quark. They get annihilated into the virtual photon, and the experimental signal is by detecting the dilepton signal on the variflow. Of course, these things actually will be break up. So in general, the Drell-Yan production process, the Drell-Yan process is in general inclusive. That means the final state of this is not well defined except for this dilepton stuff. And the key kinematic variable in this process first is the total energy of this initial state. So there was the two hadron, P1 and P2. For example, you use the PP collision or pi P collision, then you can get in the central mass of the energy. On the other hand, and another important variable is this q squared divided by s. And this q squared is just the invariant mass of this dilepton. And then this ratio between q squared and s is actually related, in the later Parton model, is related to the individual built-in x1 and x2 that's characterized the momentum fraction of the Parton inside this individual hadron over there. And the overall production cross-section is actually very simple. You can see like this. So this is the quark and anti-quark probability inside of the individual hadron, and you just time them and require the energy momentum conservation here, like a q squared equal to this S2. Of course, over there is some calculation about this cross-section. There was this interacting cross-section can be very simply done there because there was the electromagnetic interaction. And in the following slide, you can, for the student, you are welcome to take a further look, but it provides a very detailed calculation. But in some sense, this sigma 0 tilt can be simply written down something like this: 4 pi alpha squared divided by 9s. And this alpha is just the electromagnetic interaction coupling constant. Okay, so all the formula was actually very easy, so even I can do it. On the other hand, the good things for the Drell-Yan is actually the final state is the lepton. So this lepton, after it was generated, it won't interact with the hadron system again. So it won't couple together because the lepton cannot have the strong interaction with the hadron system at all. So it can be viewed as something like a penetrating probe. And however, the downside for the Drell-Yan process is actually here the coupling for this Q and Q bar here is electromagnetic. So it is well known, we learned from the very early as a graduate, as a physics, as a student studying the physics, is this phi structure constant is very small. So that means the Drell-Yan production cross-section is very small. So you have to prepare a high flux of the beam, hadron beam, and with a very target on the experimental side, so that you can get a reasonable statistic. So that is the downside of this experiment. Okay, so based on this naive Drell-Yan model, so there was a couple of the prediction. So the first one is actually scaling. That means the overall cross-section simply scale with this factor. So it doesn't scale as an individual as the invariant mass of the dilepton or with the energy. It's actually q squared divided by the x. And there will be some beam dependence and atomic dependence of cross-section, and also a prediction about the decay angle distribution if there was a quark and anti-quark, with each one is, if you consider then there's a massless and the carry has some fixed helicity and spin 1/2, you can make in the prediction of this 1 plus cosine theta square. And also the transverse momentum distribution probably only coming from the intrinsic parton at the very beginning carried inside by the hadron. So there would be probably roughly 300 to 500 MeV. So it won't be too large, because this PT has to, in this diagram, has to get conserved. Right? So the final PT for this has to be this PT only. Okay, so it won't be too large. Okay, here you are welcome to visit this site. So this list all of this cross-section major in the Drell-Yan experiment. So in general, this only list of the Drell-Yan performed by the fixed target experiment. So that was mostly carried out as the Fermilab and also at the CERN. So that was the two main sites for this Drell-Yan experiment. Okay, so this is how can we measure the Drell-Yan? So this I want to provide some basic things for these for measuring the Dimuon pair. So normally you shoot out some hadron beam. For example, here this is the original experiment carried out on the AGS. So you shoot out some hadron and interact with some target. But because of the strong interaction, you will get a lot of hadron get produced. So you have to actually shield out of this hadron. So for example, here they prepare some kind of a concrete. So all of this hadron, kaon and pion, which is likely to get the energy get converted, get stuck here. But with this specifically for muon, because it's only interact with the EM interaction, and also the Brent-Strahlen effect for the muon, for the high-energy muon, is not that large, so it can penetrate it through this shielding. Then over here you have some kind of the, for example here, hodoscope, or by providing some magnetic moment, magnetic field, you can determine the momentum measurement for the opposite sides of the muon here. So that is the experimental way. Basically, you stop all of the hadron here, and that's the dimuon comes out. Okay, so for the student, of course, if you are welcome, you can do this exercise for people. For the student working in my group, I guess it's also a required homework. Is how do you, if suppose I give you the three momentum of the of this mu plus and the mu minus, plus the information which is what kind of a beam and the target and what's the momentum of the beam. In principle, you should be able to, based on this Drell-Yan model, you should be able to calculate what is the invariant mass of the virtual photon over there and the Feynman X, and also the individual X1 and X2 for the pattern in the center mass. In the center mass systems. Okay. And then here is actually with the more advanced detector, and specifically, it's better you have to be very carefully design your hadron absorber, because the muon, even though it can penetrate through your material, but if you put too heavy material over there, this muon will still multiple scattering with your material. So they will deteriorate the measurement of the momentum over there. So that's why you were not able to see a clear bump here. So that's why Littman missed the gypside signal on here. Okay, but with the better detector and also more careful design of the hadron absorber, so you can minimize this multiple scattering effect. Then you see this kind of the Dimuon spectra. So this around 3 GeV, you have this well-known gypside bump and also psi prime. As the high mass region go beyond 4 GeV, this component is mostly this blue line Drell-Yan. But at the low mass side is the things other than J psi and the psi prime. You will also have the contribution come from the open Chang. This is DD bar. The production cross section is even higher here. It's a low mass region here. And then you also still have some random background come from the meson decay. Okay, so this is the modern, the Dimuon spectra in the modern world. And everything can be even pushed up to even large mass region. So here is, for example, is the Dimuon mass. So the previous slide is only show up to here. But if you keep increasing your photon and go to the collider mode, so you see this Dimuon can actually go up to until you see this well-known Z port, which is the so Z production and also the later on W production can be also characterized as generalized Drell-Yan. Even maybe in the narrow sense, like Drell-Yan, maybe people only talking about the virtual photon, but actually it can well extend and go to the higher energy and also go to like a Z and maybe some kind of a Z prime here. Okay, so this is also the same formulation can be also applied for the W boson and the Z boson production. That would be normally also is considered as a generalized Drell-Yan production over there. Okay, then let's see how the this previously prediction about the Drell-Yan, how it goes with the experimental check. So first is the scaling. So it's the kinematic variable. So overall production cross-section for the Drell-Yan is actually, so it doesn't matter which kind of energy it's performed or what kind of an invariant mass this Dimuon mass was measured. All the cross-section was actually lie on the universal line, scale as this variable tau. So you can do this using the proton beam or the pion beam. All of this cross-section actually collapsed on the same universal curve. So this kind of a scaling is a good success based on the Drell-Yan model. And then this A dependence. A dependence is the overall cross-section. If you right now use the nuclei target instead of a single nucleon, because as I just mentioned you, this dilepton can be considered as the final kind of a penetrating probe. So the overall production cross-section can be considered as an incoherent sum of the overall cross-section. So the target's dependence is as the power, if you check in the power of this, should be something proportional to 1. And indeed, there was the, if you're looking into this in terms of mass, in the J side region, it's actually deviate 1,1. But if you go to the pure Drell-Yan region, this alpha dependence is really close to 1. So it doesn't matter you use the pion or proton. Okay, so there is also an interesting dependence if you choose the different pion or kaon and the anti-proton. And this kind of a difference on the production cross-section can be understood by the valence quark structure of the beam inside. For example, if I using this one, so in general this is this scaling factor, and this is the data point for the pion, and this is for using the proton. So may I ask whether if you consider with the same beam energy, if you use pion, do you expect you will get a more production cross-section or less production cross-section relative to proton? Which one will give you more production cross-section? Anybody? Do people understand the question? If I use the same beam momentum, say 100 GeV pion beam and 100 GeV proton beam, and also all looking to the Drell-Yan production cross-section, which beam will give the cross-section will be larger and why? Pion? Yeah, and why? Or pion, yeah, and why? I'm sorry?
The distribution of anti-clock.
Yeah, so yeah, of course one of the ways right, because the pion had contain only 2 valence quark, and however for the proton it's actually split into 3 of them. So that's making this the proton distribution it's more relative because it has to be, there is a 3 valence quark inside here. So the X distribution is relatively soft than the pion. Okay, then it's go to the angular distribution. Okay, So just make it slightly quickly. So overall, it's looked very nicely agree with this naive expectation 1 plus the cosine theta squared. And also this similar things. And even if you move to the Z-pore, this is measured by the CDF using the PP bar. It's also agreeing very nicely about this 1 plus the cosine theta squared. Then let's look into the transverse momentum dependence. So, and then it looks like the transverse momentum dependence. So this is plotting the transverse momentum dependence as the bin energy or the center mass energy. So you see this average, the mean PT actually increase. So maybe it's starting around 300 and 400 MeV here, but the mean PT actually increased with the bin energy. So this is a kind of the deviate from the expectation of the Drell-Yan, because Drell-Yan, in the Drell-Yan picture, this mean PT only coming from your intrinsic Hadron PT. It shouldn't increase with the bin energy. So this is some kind of a failure for the Drell-Yan. And also in terms of the absolutely production cross-section. Sorry, so this is, probably you cannot see it here. So the experiment data point is here, and this line is actually calculated by this previous formula. So it has something like a factor of 2 or 3 less than the experimental observed. So there is some deviation on the absolutely cross-section. Okay, so here's a list of success. So in terms of the scaling, nuclear dependence, and angular distribution, naive Drell-Yan model is very successful. However, it's failed in giving the right prediction about the absolute cross-section and also in terms of the transverse momentum distribution. But of course, the Drell-Yan is a very naive model, as shown in the Pitt's top. You have all this gluon. So not only 2 quark and anti-quark annihilate into the virtual photon. This quark can actually emit a lot of the gluon, so they can even through the gluon talk to each other or talk to its own. So you see a lot of this complication. So then we have to place this Drell-Yan with the consideration of the QCD by putting into all of this gluon effect. And then, okay, it's actually putting in these things, it will introduce some kind of a minor violation about the Q-square scaling, but this is actually a minor issue. And also by considering this QCD effect here, for example, in the leading order, that means there is no QCD effect. You see this deviation, but then you can further apply next leading and next leading order, and it's bring to the agreement about the absolute cross-section with the experimental measure. And for the decay angular distribution, as I just told you, that in the most naive model, this distribution can be a general distribution is only limited for this cosine theta term. That is, this lambda is equal to 1, and all this azimuthal angle phi dependence is actually to be 0 here. However, when you introduce the QCD effect here, this nu and this nu will become non-zero. However, there is still a well-known relation called Lanton relation. That was on the consideration of the leading order of the perturbed QCD effect. Even though lambda will be deviate 1, and also nu will become non-zero, but this relation should be whole. So this is considered as a well-tested experimental well-test to